Okay, so I'm going to be talking about the central problem in information theory, and this is the problem of noisy channel coding. Okay, so we have a noisy channel, and we want to reliably communicate over this channel, but I look at this problem from a slightly different angle than the one we're used to than the Shannon theory. I look at this from computational complexity or algorithmic point of view. Okay, I think this is natural in its own, for its own sake, but I'll tell you at the end what was my motivation for studying this and how we can get applications of this way of thinking into problems that don't involve computation at all even. Okay, so let's just set up the model. So we have a noisy channel, so we'll denote this by W. Okay, so this for inputs X, everything is finite dimensional here. So the input I'll label X, and Y is a noisy version of X. So the probability of obtaining Y given X is given by W of Y given X. Okay, and now we have two parties, Alice and Bob. Alice wishes to communicate a message that will be calling I to Bob. Okay, so the number of messages she wishes to communicate is a number between 1 and k. Okay, so k messages. Okay, so this is the setting, and our task as a system designer is to design a system that allows Alice to communicate to Bob in a way that maximizes the probability of successful transmission. Okay, so okay, so let's model that a bit further. So what we'll do is Alice and Bob should agree on a procedure that is as follows. So Alice applies some encoding function, which takes the message, so it's a number between 1 and k, and outputs an input to the channel, which is an element in X. Okay, so this is the code, and of course Bob has to apply a decoder, okay, which takes an output of the channel and maps it to a message. Okay, so it will be useful here, especially when we talk a bit about the quantum setting, to look at the randomized version, to allow Alice and Bob to have randomized encoding and decoding, even though it's actually not helpful to improve the success probability. But for notation, it's nicer, especially for the quantum version. So I'll be noting E of X given Y, the probability that X is encoded, sorry, I is encoded into X. Okay, and same for the decoder, probability that I decode J given Y. Okay, so this is the setting, and now this defines I have a joint distribution on the random variables I, X, Y, and J, and of course I'm interested in computing the probability of success, and the success criterion here is that I is equal to J. Okay, Bob's decodes the same thing as well as what Alice sent. Okay. And again, my focus here is to try to study this problem and to try to find the optimal E and D, okay, given W and K. Okay, so we already know a lot of things about this problem, and in particular, you all know Shannon's theorem, but let me state it in this language so that we're so in this language, we look at a particular case of channels W, which have the structure of being composed of, so we have a big channel that is composed of multiple independent channels. So let's call W the small channel, and then I look at n independent copies of it. Okay, and then what we know happens in this case is if you try, what Shannon's theorem is saying is that if you try to send a number of messages that is smaller than number called the capacity, then the success probability goes to 1. But if you go above this threshold, the success probability goes to 0. Okay, so technically the second part is a strong converse. It's not Shannon that showed it, but okay, this is Shannon's theorem. Okay, so here, just to distinguish with what I'm going to be doing here, so I don't want to look at the specific case where W is multiple copies of a channel, but I want to look at the completely general case. So Again, I said I want to look at this algorithmically, so I think of the noisy model W and K as being inputs to my problem, to my algorithmic problem, and my objective is to compute this optimal success probability that I write as P success of W given and K, okay? So yeah, maybe I didn't stress enough, but yeah, this notation P success of W of K, I'll use it everywhere, so it's important to, yeah, so this is given W and K, this is the maximum success probability I can get for transmitting K messages over the noisy channel W. Okay, okay, so let's perhaps formalize a bit more mathematically what, I mean, or write it as a mathematical optimization problem, what this P success is. Okay, so it's very simple. I just, the variables of my optimization program are the encoder and decoder, so these functions E and D. Okay, and I try to maximize over all possibles E and Ds of the following function. So this objective function is just the average over all messages. Okay, so something I should say is that I will take in this talk, I will focus on the case where we assume the message is uniform. Okay, it's uniformly distributed over 1 to n. Okay, so yeah, so I take the average over all possible messages, and then I encode I into x. So this is with probability E of x given I, and then this goes into the channel. So this gives me W of y given x. Okay. And then the decoder takes y and outputs j, but I'm only interested in the probability that I is equal to j. Okay, so that's why I look at d of I given y. Okay, so I'm trying to maximize this. Of course, I cannot, I mean, my encoder and decoder are limited. They have to be probability distribution. So the constraints are that if for any I encode a message I into at most, into exactly 1x, okay, if I sum over all x's, okay, so it's a valid distribution for all I, and the same for the decoder. For all outputs of the channel y, I have that the sum over I of d of I given y is equal to 1. Okay, and of course these should be probabilities. Okay, so this is exactly my problem. And so again, I want to study it from an algorithmic point of view. Okay, maybe before getting into this claim, I should say that, so again, I repeat that E and D are the variables, so this, at least this is not a linear program, so it's quadratic because we have products of variables in the objective function. Okay, so it doesn't appear to be that simple computationally. But let's write it in a slightly different way, in a slightly more combinatorial way, to try to understand this problem algorithmically a bit more. Okay, so let me talk about this claim, which I think will not be surprising at all. Okay, so I'm just claiming that this success probability can be written in a slightly different way, and it's as follows. It's basically the only thing I want to maximize over, because I can always fix the decoder to be the best possible decoder, which is the maximum likelihood decoder. So what I want to maximize over is only over the code. Okay, so, and here what I mean by the code is a set C. Okay, it's a subset of the inputs of the channel. Okay, so the subset has to have size k because I want to send k messages. Okay, and the function I'm trying to optimize is a function that depends on W. Okay, and this function is defined as follows. It's the sum over all y's. Okay, and so this is a function that depends on the code. And for each y, I take the maximum element in the code, x and c, of the probability of seeing y given x. Okay, so yeah, I mean, I think this is very natural. Because, I mean, you're using a maximum likelihood decoder, so if you receive y, then you will output the x, which has the most probability. Okay, so by just rewriting this P success in a different way, we can write it in this way, okay, as an optimization over subsets of the input. Okay, nothing complicated here. Okay, so I'm just repeating the definition here. And okay, so now again we want to find an algorithm to compute this quantity, p success of wk. And so one natural, so okay, of course, if I want to do this optimally, I mean the trivial algorithm suggested by this notation is just to go over all subsets of size k and to compute this fw. Okay, but of course this takes exponential time. If k is large, it takes exponential time in k, and so we don't want to do that. We want an efficient algorithm for computing this quantity. And so a natural efficient algorithm in this setting is a greedy algorithm. Okay, so I construct this code in a greedy fashion, in the sense that, okay, so I want to maximize this function fw of c. So one way of doing it is I start with the empty code book, and then I add the element which optimizes, the increase of this fw. Okay, so notice that this fw function is monotone; it increases with the size of c, and so I keep adding elements to this code so as to increase by a maximum my function fw. Okay, so I won't specify the algorithm more, but I hope it's clear, right? It's a very natural algorithm. And of course, now the question is, how good is this? So this is you can show that this will not always give you an optimal code, but can we prove a guarantee on how well this code performs? Okay, and here there is a simple observation that okay, we're not solving an arbitrary problem, we're solving a specific problem, and this specific problem has the following structure, which is that this fw function is not any function from subsets. It's a function that has a very nice property, which is of being submodular. And what submodular means is that, so it's a function on subsets, and it has the following like diminishing returns property, which is that if I look at two codes, so let's think of C and C prime, let's think that C is a small code and that is included in C prime, then if I add a new code word to C, then I get more advantage than by adding this same code word to C prime. Okay. Okay, so this is the property of submodularity. And it turns out there is a well-known theorem in combinatorial optimization that says that if what you want is to optimize a submodular function subject to some cardinality constraint, then the natural greedy algorithm achieves a 1 minus 1 over e approximation factor. Okay, so in particular for our problem, if we try to find the code in a greedy way, then we have the guarantee. So of course, in general, it will give you, it will not be as good as the optimal code, but you can show that the success probability it achieves is at least 1 minus 1 over e times the optimal success probability. Okay. Okay, so yeah, we find an efficient, like polynomial-time algorithm for computing the success probability, but that achieves this factor of 1 minus 1 over e. Okay, so the question now is, okay, is it possible to find an efficient algorithm that is maybe a bit more complicated than this greedy algorithm, but that is still efficient and that obtains a better guarantee? Okay, so it turns out that no, 1 minus 1 over e is the right approximation factor. And this is due to an important result by Feige in 1998 that shows that there's no polynomial time. Okay, so I mean, it's for a problem called maximum coverage problem. And it shows that for this problem, the optimal approximation ratio is 1 minus 1 over e, okay, unless p is equal to np. Okay, so let me briefly say what the uniform maximum coverage problem is. So it's a well-studied problem in combinatorial optimization, and the input here is that you have a family of subsets, okay? And I used the suggestive notation to see that it's basically the same problem as the noisy channel coding problem, is that you have a subset, you have a family of subsets, they're all subsets of the set Y of outputs, Okay, and we have one for each input. Okay, for each x, we have a subset. And yeah, I'll look at the uniform version of that, where all the subsets are assumed to have the same size exactly. Okay, okay, and you're also given an integer k. Okay, and your objective is to choose k of these subsets that cover the maximum number of people. Okay, that cover the maximum number of elements in Y. Okay, so natural problem. And there is a very simple reduction from the maximum coverage problem to the noisy channel coding problem, where you just say that my noisy channel is defined as follows. So for an input x, I choose uniformly at random one of the elements of the subset. Okay? And so, yeah, I wrote so 1 over size of x. And then it's easy to see that this function, fw of c, which we're trying to optimize, is exactly, I mean, it's proportional to the size of the union of the subsets Sx. Okay, so basically the uniform maximum coverage problem and this p success problem are exactly the same up to multiplicative factor. Okay, or rather, we can encode the maximum coverage problem in the noisy channel coding problem. Okay, so as a corollary, we get that there's no polynomial time algorithm achieving an approximation ratio that is better than 1 minus 1 over e. Okay, so basically, yeah, if we're interested in the approximation factor for this noisy channel coding problem, it's basically, yeah, it's 1 minus 1 over e. Okay, so okay, let me now move on to okay, or let me say that, so what we obtained is a greedy algorithm, so an efficient algorithm for obtaining what are called inner bounds or achievability result. So we have an efficient way of obtaining codes that are guaranteed to be not too bad. Okay. What about, okay, now let us look at the converse side of things, and let us try to obtain upper bounds on this maximum success probability. Okay, and now perhaps let me mention my motivation for studying this problem. So I come from quantum information theory, and my motivation for studying this question is that I would like to understand how much in this setting where you have a classical channel and you want to send a classical message even, how much does entanglement between the sender and the receiver help you in performing this task? Okay, so let me set up a bit. I won't talk too much about quantum, but like only a couple of slides. So the setting is exactly the same, but now the difference is that, or okay, let me first start with a classical version of that. So you can ask the same question, but suppose the encoder and decoder, or Alice and Bob, have shared randomness. Okay, so they share some bits from before, but okay, it's easy to show that this will never help them in optimizing the success probability, because you can just take the optimal, I mean, it's just an average over the success probability, and you just take the best one. Okay. Okay, so now you can ask the same question: what if they share entanglement? Okay, what if Alice and Bob share entanglement? And then the question is more tricky. Entanglement is not, of course, cannot be written as an average in this way, and it's more complicated. So let me say how mathematically we model them having shared entanglement. So we have some Hilbert spaces. H, we'll call them the same, one on Alice's side and one on Bob's side. So both are called H. And we assume that they share a state. Okay, so it's an arbitrary state between Alice and Bob, and we don't bound its dimension. Okay, H is of arbitrary dimension. We can assume finite. Okay, and then what they perform, the encoding map in this setting is what's called a measurement that depends on I. So as a function of the message I would like to send, so Alice performs a measurement on her part of the state. Okay, and this measurement gives an outcome, and this outcome, Alice feeds it into the channel. Okay, this measurement outcome is exactly the input of the channel. Okay, And Bob does the same. She performs, as a function of y, the y she gets, she performs a measurement, and she gets a j. Okay, and that's her decoded message. Okay, and yeah, the question I'm interested in really is how much does entanglement help in this setting? Okay, so yeah, if you're familiar a bit with Bell inequalities and this kind of setting, it's a similar question that we ask here, but yeah, in this setting of channel coding. Okay, and again, I'll denote P success with a Q for the quantum version of the success probability where they're allowed to have entanglement. Okay, so let's give some examples before getting into how much entanglement helps in general. We know of some examples where things either don't help or help. So we know that in the limit of when you take n independent copies, we know that the entanglement does not change the capacity. So the capacity stays exactly the same for if you allow entanglement between Alice and Bob. Okay. This was known for a long time. But we know of some channels, namely, for example, this one, where entanglement can help. Okay, so namely, okay, this channel, yeah, doesn't matter what it is exactly, where we have that the optimal success probability for sending here a bit over the channel is 5/6, but if you have, sorry, there's a typo, that's supposed to be PQ, P quantum, the success probability is a bit bigger, okay? And yeah, again, my objective is, like, is this the only example where it's bigger, or what is the extent to which quantum can help, and in which settings, okay? Okay, what is this? Okay, so maybe let's write the optimization programs next to each other so that we see the links. So you see, I mean, that's why I wrote it in this randomized way so that the quantum version and the classical version looks very similar. And the difference is that instead of having these E of x given I, which are scalars, now they're operators on a Hilbert space of arbitrary dimension, and we're optimizing over those. Okay, so I changed non-negative numbers to positive semi-definite operators. And yeah, of course, in general, this seems even harder to solve, right? Because I don't even have a bound on H. It's not clear whether it's computable even, this quantum success probability. Okay, but yeah, so again, the question yeah, okay, so let me first make a clear observation is that I mean, with entanglement can only help me, right? It cannot, I mean, and the way to see it mathematically is that I can always take this Hilbert space to be one-dimensional, and I will get that these E's are just numbers, okay? And so the question is, can I bound things in the other direction by saying that the quantum success probability is bounded by some constant, let's say, times the classical or the unentangled success probability. Okay, and okay, maybe I can say right away that we'll see that this constant is actually 1 minus 1 over E, or 1 over that. Yeah. Okay, so yeah, in order to prove such a result, what we need to do is to find an upper bound on this quantum success probability, because you see this thing is not tractable at all, so we would like to find a tractable upper bound on this quantum success probability. Okay, so let's first maybe try to find a tractable upper bound for the classical version of the success probability problem, because this seems easier. It's a combinatorial optimization problem. Okay, so a natural way of obtaining good upper bounds is to define like semi-definite or linear programming relaxation. Okay, so in this case, there is a natural, if you look at this problem of optimizing FW, there is a natural LP relaxation to that. And yeah, of course, in FW, you have this maximum of x in C, which you can replace by some linear version of that. So you replace it by this variable Rxy, but then this Rxy is bounded by Px. So you can think of Px as the fractional version of the code. Okay, so these px's, if you want, is the probability of having x in the code, so this should sum to k. And yeah, you have a natural LP relaxation. Okay, so this is just saying that it's a relaxation. And actually, in fact, you can prove that this relaxation is even a relaxation on the quantum version. Okay, so the quantum success probability is also upper bounded by this LP. Okay, it turns out that this LP actually has other interpretation, and it's actually quite important. It's so first, like a kind of operational interpretation of it is that it corresponds to an optimal success probability for sending k messages over the channel, but with a non-signaling box, which you can think of it as a generalization of entanglement. Okay, this was shown by Matthews. And this actually LP also corresponds to a very well-studied bound that is known as the Polyansky-Poor-Verdue bound, which is used a lot in obtaining finite block length bounds. Okay, so okay, so let me maybe recap things and say a statement of the main result. Okay, so yeah, so we have all these. Okay, let's look first at the two middle quantities. These are the things we're interested in. It's the success probability for sending k messages over the channel W. Okay, this is with no shared entanglement. And then there's the quantum version with shared entanglement. So this is bigger. And we have the kind of computationally efficient proxies of these two things. So we have on the upper side, we have the LP relaxation. Okay, and on the lower side, we have the greedy algorithm, which gives you an actual code. Okay, so yeah, again, P greedy is just whatever the greedy algorithm gives you. Okay, and what we saw before is that we can give a guarantee on how well the greedy algorithm performs. So we can lower bound the P greedy here by 1 minus 1 over E times the success probability, times the optimal success probability. But okay, this doesn't tell us much on the actual problem we were interested in, which is to relate the two middle guys, right? The quantum version and the classical version. So for that, we give basically an improvement of this inequality and say that even this 1 minus 1 over E factor, you can show it even between the two, the leftmost part, which is the greedy, and the LP part. Okay, so the difference, the ratio between the greedy and the LP is 1 minus 1 over E. Okay, and okay, even you can improve that a bit by saying that, okay, suppose yeah, I have that the value of the LP gives me some value, and even if I want to, so I can construct a code that is slightly smaller, but that will have an approximation factor that's better than 1 minus 1 over E. Okay, so yeah, we can think of it as yeah, you can put L is equal to K, but you can even have the general version. Okay, so this shows that, in particular, entanglement cannot help by more than a factor of this 1.58, so 1 over 1 minus 1 over E. And this also shows that this Polyansky-Poor-Verdue bound is optimal up to, or is tight up to this 1 minus 1 over E factor. And yeah, okay, if you're wondering whether this factor is optimal, it is. It cannot be improved, so there you can construct a channel where this factor is achieved. I mean, because these, I mean, the LP bound and the greedy bound are efficiently computable, so these are nice quantities you can work with, and so there are some channels for which you can compute these exactly, and this is tight. Okay, so yeah, maybe I don't have much time to go through the proof idea, but maybe let me mention that actually, after proving this, we realized that this was in a paper that even predates submodularity. So our thing, at least for the case L equals K, follows from, I mean, is a special case of a problem called the location problem, which is well studied in combinatorial optimization. And yeah, they basically showed, they considered the LP, they considered the greedy, and compared both things, and they showed a similar bound. Okay, we give a self-contained proof in the paper, but I'll skip through this, perhaps. I have 5 minutes, okay. So that's not correct. Okay, maybe then I can go a bit over it. Okay, so let me try to give an idea of the proof. So, okay, perhaps one ingredient of the proof is to generalize, I mean, this function fw is defined on codes, right? So it's a function defined on codes, and so now we're defining a fractional version of this problem, an LP relaxation. So it's useful to define a fractional version of the function f. Okay, so yeah, again, think of p as a fractional version of the code, and you can define this fw of p in this way. So in particular, if px is 0, 1, then this is exactly, it takes the value of the corresponding set. Okay, so it's a generalization of this fw. And of course, the LP version, so the success probability for the LP is given by the maximization of this function fw. Instead of looking at just subsets of size k, you look at these fractional versions that sum to k. And okay, you can show this lemma relating the fractional version of this function to actually the value it takes on subsets, okay, C actually for any subset, and relate this by, you add a factor that is k times basically whatever you gain by adding an element into this code. Okay, so I won't go into the proof of this lemma. But basically, once you have this lemma, it's quite immediate to show that the greedy algorithm, you can relate the greedy algorithm to the LP, and basically you take the running of the greedy algorithm, so it starts with the empty set, and then it includes an element, etc., until you have L elements. Okay, and you just apply the lemma to one step of this greedy algorithm. So let's say the tth step, and you see that this maximum over all x's of C union x, if you start with CT, then this is just CT plus 1. This is FW of CT plus 1. Okay. Okay, just rearranging the term, you get 1 minus 1 over k. And then applying this inductively, okay, for every t, you get a 1 minus 1 over k to the power L for the Lth step. Okay, and yeah. So yeah, you see that the maximum over p of fw of p is the value of the LP. So you have it on both sides here, and so you can relate it to the greedy algorithm. Okay, simple proof. Okay, so just to summarize, so yeah, we looked from an algorithmic point of view to the problem of reliable transmission over a noisy channel. And we saw that there is there's an efficient 1 minus 1 over e approximation. This is both from a lower approximation and an upper approximation, in the sense that you can give this greedy algorithm, which gives you an actual code, and you can also give an upper bound on the maximum success probability. And actually, these two things are bounded by 1 minus 1 over e. Okay, and as a corollary to that, if you want, we showed that the two quantities in the middle, which is the quantum version and the classical version, are apart by a factor of 1.58 at most. Okay, and so I really think this is an interesting point of view to look at, and yeah, my message is that I think there should be more work on looking at these information processing tasks from an algorithmic or computational point of view, and I think we can gain some very useful insights, especially use tools from the approximation algorithms community and combinatorial optimization. Okay, thank you.